We're ready to roll on to our last but definitely not least presentation, where we're going to focus on the unintended consequences of excessive inventory on capital projects. And it's been my experience that project leaders, I know it was the case for me, are pretty much blind to the fact that excessive inventory on project drives longer schedules, cost overruns, accelerated cash flow, all negatively affecting the return on investment. On the other hand, if you don't have enough inventory, the project will suffer. So in the spectrum of too much, too little, is there an optimal point? What are the drivers of this optimal point? Can it be determined? If so, how? Our next presenter, who again needs a little introduction, Roberto Arbalu, who is also tackling these questions and debunking the common belief that running projects with high levels of inventory represents a best practice. So again, a lot of you already know him, but I'm going to introduce him. Roberto is our Senior Vice President of the Technical Services at Strategic Project Solutions. He has over 20 years of experience in delivery and optimization of major capital projects in the oil, gas, mining, industrial, and civil infrastructure sectors. He's authored many papers that have been published in various trade journals and presented at conferences around the world, including being a lead instructor for Stanford's SciFi SPS VDC certificate program. Roberto holds a master's degree in construction engineering and management from the University of California, Berkeley. So with that, I'll turn it over to you, Roberto, and come back for Q&A.
Thank you so much, Gary, and good afternoon, good evening to everyone attending the PPI Technical Conference. Today, we're going to expand on a topic that I have heard previous speakers have touched on, and we're going to dive deeper on these unintended consequences of excessive inventory on capital projects, right? And we're going to start doing it by exploring two things. First, it seems appropriate that we look at what inventory really means, okay? And in order to do this right, we're going to use a production framework based on operations science to define what inventory means. We're going to go back to basics a little bit, purposely. And the second idea is this idea of excessive, right? Obviously, this alludes that there is some point that beyond that point, everything becomes excessive, right? It could be the other side, which is not enough, right? And so where is our optimum point, right? What I bring you today and what you will see in the paper that you will be able to download from the PPI website is that there are specific ways on how we can calculate the cost of having excessive inventory. What are the implications of operating based on excessive inventory? But let me start first with what do we see across the industry globally, right? And the common denominator, there are obviously exceptions, but the common denominator is that we see, a behavior, get as much as you can of everything you can as soon as possible, as early as possible, right? And almost just in case something happens, right? As the project gets more complex in size and, in terms of capital investment, we see situations like this picture here, where we have laydown areas, sometimes in addition to the ones we have on sites, right? We have some off-site laydown area, or even warehouses, although I'm not showing a picture of a warehouse, right? But significant volumes of materials, right? And so the other thing is that every time that we talk about inventory in construction, people relate inventory to stocks of materials. So the question is that the only perspective behind inventory, right? I don't want to necessarily focus on semantics here, but if you look at inventory and stocks and you look at, formal definitions semantically, inventory and stocks are typically synonymous, right? And so when people refer to inventory being a stock, there's nothing wrong about it. But the question is that the complete picture of inventory, okay? And the short answer is no, it is not, because inventory includes another key component in addition to stocks, okay, which is work in process. And work in process is typically, and this is based on my personal experience, is certainly a blind spot across those of us that work in engineering and construction, and the implications of operating with excessive work in process. So I repeat, when we think about excessive inventory, we need to do it from the point of view of excessive stocks as well as excessive work in process. So we will show some examples and get a bit deeper on this topic. But if we look at a generic production system or production process like this one, James talked about it earlier, so I'm not going to spend a lot of time on this. But if we have multiple operations, there's work that at some point is within each of these operations, right? Work that is being processed, right? But at the same time, there's work that is waiting to be processed in between operations, right? And that work is waiting because in this example, let's say between operation 1 and operation 2 is not able to take that work that was actually released by operation 1. That's just one example because of probably a lack of resource, right? So in production, we need to be extremely careful about these queues because typically work will accumulate quite significantly. And the summation of all these components, right, the work in these 3 operations plus the work in these triangles will be what we will call the working process. And working process is measured as the number of units, right? So if this is a piling production system, I'll bring to you an example of piling, a couple of examples of piling later on. And I have at any given time, almost like taking a picture, if you will, of this production at some point, production process at some point in time. Operation 1, let's say that is doing 1 pile. Operation 2 at the same time is doing another one, and operation 3, another one, that we have 10 piles on the first queue on the left and another 10 on the queue on the right. We have a total of 20, 10 plus 10 plus 3. We have 23 piles being processed, right, in working process. An inventory will include stocks. In this case, we, following the example of piles, we have a stock of piles that need to be entered the system, and we have an output stock of something that these 3 operations produced, okay? If we want to expand this picture, right, in a production system like this, is still generic with more operations. The set of operations on the right, this subset of the production system, will have its own working process, right? This flow number 2 that depends on flow number 1, right? And so working process can be isolated according to what portion of the entire production system we're talking about. In this case, in the middle, we have a stock of the output of the first one, a stock of work. It could be as a requirement or as an input for the next one, okay? We'll expand on this in a minute. Now, here's another thing that happens with inventory. When we talk about, in general, about production, there seems to be, for some reason, some underlying mental models that production is just physical, right? We can have, a stock of skids, modules, as Boshin was talking about, that are ready for shipment. We can understand, working process as a number of skids being fabricated or assembled. Nothing wrong there, right? But there's also the non-physical production. Engineering is an example of non-physical production, right? And so we need to be careful that, inventory not only applies to physical, it also applies to non-physical, right? We can have a stock of engineering packages ready for construction, or a specific working process in a system, like X number of deliverables that are being produced, okay? And this is the case of this example. This is an engineering production system, right? There's nothing physical, if you will, in this production system, and it produces isometric drawings, right? So if you look at the right of this production system, there's a stock of fully completed isometric drawings. Isometric drawings include sections of pipes in industrial type projects, sections of pipes where you do different, you do a stress analysis to the pipe, right? And what you see here, you see three different production process in the production system that these isometric drawings go through. The one below, is a bit more complex, and the one on the top, certainly much simpler, right? And so each of them will have their own working process, number of isometric drawings at any given time, okay? So if we want to compile all these ideas, as the first thing we said we will do is to define inventory. Inventory, what really flows through a production system. The work is actually done to it. It could be stocks, it could be work in process, work being processed, work waiting to be processed, generally due to a lack of resource. On the stocks, it could be information, something non-physical, could be raw materials, it could be finished goods, could be assemblies, right? But also could be work waiting, right? And this is sometimes what brings a bit of confusion, because some project team established some sort of policy. James mentioned this based on a question that he was asked, but the stocks could be a stock of work, okay? Waiting that being accumulated based on some policy, right? We have some examples for you in a minute. So these pictures are how we see typically stocks in our projects around the world, right? The one on the left is a stock of pipe spools that were already fabricated and assembled, that are just waiting there, ready to be installed, right? And as you can see at the end of that photo, there's a crane, mobile crane with a crew that is actually looking for the right one, right? Pipe spools are a very interesting example because they go into a very unique position on site. So you could have a lot of stock, right? A lot of quantities of spools like you see in this photo, but if you don't have the right one, it's going to be really hard for the site team to actually establish a sequence of installation. When that happens, they have to shift to another work front because they don't have the right one. And the consequence is that you have a lot of work fronts open, right, but not completed because you don't have the right one, right? On the right, it's the complete steel structure of a building, right? The only crew you see here is the one installing the staircase, but you don't see any slabs, concrete slabs, or you don't see any facade, for instance, right? And so in that example, someone has made a decision to build the entire structure based on some policy before the work is actually released to the next crews or the next discipline or craft, okay? And so stock could be stock of materials, but it could be also a stock of work waiting for a specific reason that someone decided to, have certain level of work before the production process continues. Consequences, right? And when we talk about a stock of materials, right, it comes to a price, right? I think in the previous session, somebody asked a question, right? The cost of keeping excessive stocks, right? I'm talking about one of the components of inventory. Excessive stocks is just a long list. I don't want to go through every single one of these, from double handling, from having to preserve, right? Sometimes we get equipment, not just structural steel, for instance, but the equipment has to be preserved in order to maintain the warranty and the quality, right? The actual cost associated with the infrastructure, the laydown areas, offsite or on-site, or the preparation of these laydown areas or warehouses as well. Sometimes we see that along the production system, the value chain, there are stocks that are actually being kept for us, the project team, let's say. But if we have design changes, they can become actually obsolete, okay? When we say theft, we don't mean, thieves stealing the equipment is that or the materials, excuse me, but the material that was actually allocated for one team is now being used by another team. This happens once again as the project gets larger, it becomes pretty common, right? And last but not least is the amount of cash tied up when we deal with extreme cases of inventory or excessive cases of having more stocks than needed, right? So there is a cost associated with keeping these. And, we need to remember that the price we pay for an item, whatever that is, equipment, steel, is not the cost, right? And if I go back here, there are a lot of reasons why we start getting cost escalations or cost increase, excuse me, because there are a lot of things happening when we operate with excessive volumes of stock, okay? But let's switch now to the other component of inventory, which is work in process, right? Work in process can manifest in real life in projects in many different ways. These are just a couple of examples, and we will dig in one of them. But the one on the left is, I took this picture on a industrial project in the United States when we were doing a visit, and we saw that there were some valves missing, as you can see here where my mouse is. There's one here missing, another one here, and so forth, and they're all over the place, right? But the team actually went ahead and fabricated these threaded rods in order to calibrate the alignment of the pipe, right? And each valve has, like, I don't know, four in this case, four to the measurement threaded rods that someone has to fabricate, put in place, right? Align the pipe. And what typically happened, in this case, actually it did happen, is that the team gained progress of having the line completed because of that, right? And so from an earned value management perspective, you can see the S-curve going up, and people might think that it's actually good news because we have more progress. But at the end of the day, when it comes to finishing something like this, some of those hours might have been already accounted, and now we have to do a lot of work to finish. Let's say if you get to 90%, to finish the last 10% of your S-curve take a lot of time, and those sometimes are hours that are non-progressible hours, okay? And so plus the cost it takes to take the rods out, right? Put the valve, realign, and so forth, right? So there are hundreds of other examples, but if you look at the one on the right, which is about piles, right? And you can see in this photo piles that are already driven, but you don't see yet, these are precast piles. You don't see these piles cut or cropped, right? Even if you look at behind these equipment, there's actually hundreds of them on this particular construction site. So I'm going to dive deeper on this example, conscious of time, and show you guys. This is a true story, by the way. This is a real project in the world, right? And at some point during the installation of the piles, during the construction, the team shared this data that you see in this table. A total of almost 28,000 piles, 22,000 roughly were already driven into the ground, 7,000, a bit more than that, were already cut, and cropped were 0. If we translate this into a production perspective, like the map you see below with queues and stocks and the operations in orange, we can conclude the following, right? If we don't have any crop piles, it means that there's 0 piles in that stock on the right, okay? And it means that these 7,600 or so piles are either waiting in that triangle ahead of crop, or they are being cropped, right? There's a high probability that most of these are actually in the triangle. Nothing is being done to it. They're waiting to be cropped. If we do the math and we have 22,000 already driven, it means that approximately 15,000 are either waiting to be cut or being cut at that point in time. right? And the difference between the total tell us that there's approximately almost 5,000 that are either waiting to enter the system, the production system, or being driven in at that point in time. What is the point here? That if we add 15,000 and 7,000, we have approximately 22,000 piles in WIP out of the 27. That will be about 80% of the total amount stuck in the system, okay? And the other thing that is obviously very important is that the throughput of this production system is 0 as a production system. The drive operation probably has a very high throughput, but the system has throughput 0, right? This system is not releasing any piles to the next craft, right? The foundations, let's say, right? They're not receiving any work. And when you have work in process that is excessive, right? This example is not meant to establish the optimal. We will talk about optimals in a minute, right? But every time that we have work in process that is excessive, right? The time it takes, because of the time goes into the queues, for a single pile to travel that system, right? Start getting really long, right? And that's why there are implications on a schedule, okay? So you can look at any production operation or system in your projects this way, look at the data and see what is happening with your work in process. Work in process is part of inventory. It's inventory of work. This is another example of piles in a different region of the world that includes 2 types of piles, top and pencil piles. And you can see in this production map, there's a portion that is about fabricating and delivering, a portion that is installing, right? And the team was interested in answering the question, how much stock should we have, that red cylinder, how much should we have at any given time? What should be the stock size, right? And one of the first questions is to understand the demand, right? What is the demand that the installation requires, right? In this case, you can see a profile. The green bars relate to top piles, right? We need approximately 14 piles per day. That's a number per day. And the pencil piles get to a point where the maximum demand is about 18 per day, right? And so the question is, how can we calculate, not estimate, precisely calculate what should the size of that stock be, right? The team created a model, a production system model, concentrating on answering, that was one of multiple questions, but I'm just going to focus on that particular question on the size of the stock. Similar to what Boshin shared earlier on the previous presentation, one of the analyses that was conducted here was to understand the stock trade-off, right? For that particular stock in red on the previous production process, right? What you see here are different curves. Each of these curves represent a different frequency of ordering the piles, right? So if we look at 2 orders per week, by the way, this means 2 orders per week, which is the blue one, is more frequent. That means that we need less stock. If we go for 0 orders per week or 1 order every 2 weeks, that's another way of looking at this. It means that we need obviously a bit more volume of stock in order to keep up with the demand, right? And something in between is 1 order per week. When it comes to analyzing stocks, every point in these curves could be an optimal point. I repeat, every point in these curves could be an optimal point, right? I can go for 99% fill rate, and that fill rating means what percentage of the demand the stock is going to be able to respond to, right? Because the fabrication facility of these piles was actually pretty close to the site, and the ability of the fabricator to have some stock in their facility, right? Remember, we're analyzing the size of the stock on site, right? The the decision was to go for about 90% fill rate, okay, as the optimal policy for that stock of piles on site. Now, that means that approximately will equate to this amount of cash in that inventory size. But I will show you in a minute what this really means. What you see on the right is a curve that analyzes or translates what you see on the left, but in terms of cash over time, right? The green is the optimal stock policy, right? The red one was actually a policy that the team, based on their experience, established before this analysis was done. And as you can see, it's much higher. And I will talk in a minute on a different slide about the blue, okay? What happened with the proposed policy? There's a story behind that, okay? And so we can systematically calculate, okay? This is not Roberto's opinion. We can calculate, according to fill rates, what should the size of the stocks be, okay? This is not work in process. This is the stock, okay? This is an example of the stock. According to multiple factors, including variability in the system, variability in demand, what is the actual demand, and other factors. Not only that, we can determine what should be the reordering point or the reorder point, right? Meaning that if we have two, in the case of pencil piles, when the stock gets down to 12 units, I am going to order a bit more. How much? How many more? 45 in this case, right? If the top piles get to 14, I order 35, right? So I'm going to maintain my stock levels according to the demand within those boundaries, okay? According to 2 orders per week. And so why is all this relevant? And I think there was a question, once again, on the previous presentation that this might actually be helpful for you who asked the question, and for everyone on the conference, is the implications, right? And so, as you can see here, based on the experience, the team used a stock or was planning to use a stock equivalent to $200, almost $40,000 worth of cash, right, on those piles. The analysis indicated that without compromising the installation rates and the progress on site, they could actually operate with, less than 80% of that, right? Equivalent to 32,000 almost worth of stock. And the reaction of the team was, well, that's too little. They started becoming a bit concerned about it, say, can we really handle that? What if we don't want to do the optimal stock policy, basically, they said, right? They were nervous about it. And so they said, well, what if you double that, right? And we sort of arrived to a number close to 68,000. That was the final decision. But even in that case, that number or the volume of the stock represented 70% less. Not only the volume, but also the cash tied up. Okay. So let's move into another example. We talk about the stocks and how can we calculate those stocks. Now we're going to talk about work in process. James and Boshin and also Todd mentioned different examples, but in this particular, I bring another example on a piping production system, right? On the left, you see a stock of pipe spools. There is a series of operations that are required to install these pipe spools, different types. And it gets to a point where we can do hydro testing and reinstatement, right? When you hydro test a piping system, you have to take some pieces apart and then put blinds and other components, and then you have to reinstate the system and get ready for the installation of other components like heat tracing, installation, and do testing, and then ready for commissioning. But conscious of time, we're going to focus only in this yellow portion of the production system, or the entire piping production system on a construction site. And we're going to look at how the team determined how many hydro tests also including the reinstatement, they needed to be working on at any given time in order to meet the schedule, in order to meet the demand that it is imposed by the schedule. And after creating a model, going back to what James presented, right, a model of the production system, the team actually determined the following: that the demand they needed to achieve was about 2 orders every 3 weeks, right? And so we have approximately an average, we have a 0.60, sorry, 2 orders every week, excuse me. And we have 0.67 hydro test packs per day, right? That the team needed to meet, right? That the system needed to have some throughput, right? Actually, that accounts about three packs per week. And so they were able to generate a flow analysis like this with the magenta curve representing the throughput as a function of the working process, and the red line represented the cycle time as a function of the working process as well, right? Both of them including variability. When you see that intersection of the green line with the throughput chart, right, for that particular demand, first of all, the system is capable. It does have the capacity to meet the demand. Otherwise, that magenta curve will be below the green curve, which is not the case. And it is telling us that the optimal amount of work, the working process, an element of inventory, right? The working process should be around 21 packs. So in that yellow portion of the system, I need to be working, including the reinstatement of the systems, on 21 hydro tests at any given time in order to keep up with what is the requirement of the project. So, but there's also other implications, right? If I go lower than 21, right? So basically lower than 21, the throughput is not enough. It goes below, let's say, close to 0.6, right? And I don't meet the demand, right? And so that's the other side of not working with the right amount, not excessive, but, you know, too little, right? Or not enough inventory. But if I go, let's say, to 30 hydro test packs, right, I can get a bit more throughput, right, which is this point here. I can get 0. Probably 70 or 75 packages per day, okay? But the implications are on the cycle time. The cycle time starts going up really rapidly, and I can move from 31 in this case per pack, including the reinstatement, to, let's say, my example of 30 might go all the way to beyond 40 days, right? If I double that working process to 40, the number of days that each package approximately will take is close to 55 or so. Okay, so there are implications on working with excessive working process, right? Not only in terms of the cycle time, as this curve shows, but also in terms of when we have more working process in the system, we tend to put more resources to work on that working process, and we start spending more money trying to deal with WIP, okay? Now, you might say, look, is this really a safe to be on, let's say, 21? Do we go for that optimal? Well, what happens if additional variability kicks in, right? So it would be more prudent to go for an optimal working process level of, let's say, 22, 23 packs per day as the optimal, okay? So in summary, and I finish with a couple of ideas. When we have a production system, inventory is the combination of stocks and WIP. We have very specific means of how we can calculate the size of stocks according to multiple variables, right? And determine what should the optimal be. Why should we have a stock that is, let's say, $400,000 worth of cash to $50,000, right? And also the working process, right? We need to be conscious that it's also part of the inventory, and there is a specific way using operation science on how we can calculate it, precisely calculate it, not guessing, right? Not a subjective opinion, right? An analysis with specific calculations. The unintended consequences of excessive inventory, both stock and WIP, are obviously a significant amount of cash tied up. It costs us more to do what we need to do. It takes more time, like the example of the piles that I was showing earlier, and there's significant health and environmental and safety risk, including quality, when it comes to both WIP actually and stock. Okay, so I leave you with this what to do next sort of suggestions, right? I think that in order to be able to determine what are the optimal levels of stock and WIP as part of inventory and production system, we need to map them out and we need to analyze them, okay? The good news is that we have very effective means of determining these optimal levels. Now we know what excessive means. Now we know what less than optimal means, okay? Not enough. And later on, control and improve what happens with these production systems, because the levels of inventory and WIP will also be changing over time according to variability. So I leave you with those ideas, and thank you, Gary.
All right, thank you. Got a few questions for you. We're going to take a little bit of time to do that. First
Okay.
one, interesting question. Is there a way to combine this process mapping with the last planner system?
Well, the last planner system, so this, what we're showing here is a way of understanding production systems, right? What we see, I personally see all the time, is that the last planner system is being used to create schedules, right? It's being used to create schedules and try to control those schedules, right? What we're showing here is not that. We're showing an actual production system where we explicitly see and are able to calculate what is in those triangles, right? And the impact of work waiting, right? We in the industry, and I want to also emphasize this, although I didn't mention it, we tend to focus a lot on capacity not waiting for work, but we don't put enough emphasis on work waiting for capacity, right? And I think we have learned that, you know, it's a very strong productivity focus in the industry versus a production focus. But last planner is not about what we're showing here, right? This is more on understanding a production system and be able to systematically measure WIP and stock.
Okay. Another question for you. Would cutting and capping those piles before they were actually needed serve any purpose? Or is the issue really that the piles have been purchased before they were needed at all?
Well, in some cases, you need to deal with unknown soil conditions, right? And so some of the piles could actually be driven a bit further than other ones. And so cutting them in advance could be explored as an option, but it will bring some risk as well, right? But that example of the piles was actually about working process, right? It shows also stock of piles, and because they were precast, they were standard piles. But the point of that example was, you know, what decisions that team made that created so much working process, right? With no throughput out of that system that will release work to the next trade, right? I think that's the point we want to highlight in this paper is, do not be blind about the impact of excessive working process in a system. We're not saying that inventory needs to be zero, or that stocks needs to be zero, or the other component of inventory needs to be zero, in this case, working process, because you will have throughput, no throughput in a specific operation, right? But it's about working process.
Yeah, and I would say, based on my own experience, Todd or Roberto, and you may have, it might have been my project, I don't know, but it's a very similar project. In hindsight, we saw that we added a year to 2 years to the schedule to amass those piles in the ground to shift them in one big batch to our foundation crews. We thought we were protecting the foundation crews from bad things happening in the course of the work. We shot ourselves in the foot and added 2 years to the project schedule, which was very negative to our return on investment. So that's just a perfect demonstration of the cost of WIP.
And it's also, Gary, now that you mentioned that, we have to be really careful about what, the S curves are telling us, right? Because in that example of the piles, maybe the S curve was actually, and I mentioned it during the presentation, but I just want to come back to it again. The S curve might be showing like hey, we're doing well, right? It's because the driving operation is gaining the most progress. It has the higher weight in the progress, but in the system you have a lot of work being stuck, right? And there's nothing coming out of it.
Yeah, totally understand. So since WIP is, clearly a leading indicator of project performance, and at least on most projects, WIP is not even seen or measured. What do you think people can do to start incorporating WIP in the way they make project decisions?
Well, I think that a lot of the decisions about WIP are really made earlier in the project delivery process, during engineering, right? And so during engineering, we not only engineer, we make decisions about how we're going to produce later on, right? And so I think that paying attention to WIP is not just when we start building something. Paying attention to WIP is in early phases of engineering. We can model these production systems during engineering, right? We could have concurrency of designing the asset, the building, the facility, the factory, whatever that is, what they're building, and designing the production system, right? And so that's number one. And the second one is, you have already a production system that is active. Probably that example of the piles with 20, almost 28,000 piles is a great example, because that is almost like taking a photo of that production system that is operational and analyzing it from a production perspective, and really understand, why is it behaving this way? Why is it that we're not getting more throughput, right?
Yeah, very good. So one last question, then we're going to have to close it off. Did the reality of your two examples meet the forecasted?
Say it again, please.
Did the reality of your two examples meet the forecasted?
So I actually talk about the stocks. So in the case of the stocks, the stock of piles, remember that what they decided to do, the forecasted, was to have almost $250,000 in the stocks, right? Worth of cash, right? And so we were trying to influence that forecast, right? And say, look, you have other options, right? Let's see what those options are, right? Without compromising the installation rates, right? And so the analysis, actually, you could argue, that changed completely the forecast, right? By design, not by mistake, right? Completely the forecast, right? With a much lower stock size, right? The second one, on the hydro test packs, there's always variability when it comes to execution, right? Everything we do, and other speakers have talked about it earlier. And so when you determine what should be the working process level within a section of a system, you have to put some mechanism to control that. If you don't control WIP, even if you can calculate it, right? If you don't control WIP, there are different. My presentation is not necessarily focused on the means to control WIP, but if you don't control WIP, that can actually increase without you noticing very rapidly, right? The good thing about WIP is that it's really a leading indicator. If you see WIP today, or excessive WIP today, you will see longer cycle times tomorrow, right? Where cycle times become a lagging indicator, but WIP becomes a leading indicator. Okay.
I think on that thought, that's a good one to land with our audience because that's a fact. So thank you very much, Roberto, for the paper. It's a great paper, and I'd encourage everybody to get a copy of it and read it.